honored to introduce Dr. Stephanie Lackner. She's an assistant professor in economics at the IE Business School and the School of Global and Public Affairs at the IE University. Her research interests revolve around natural hazards, the socioeconomic impacts of disasters, and geospatial data analysis. And today she's going to talk about her project, a new approach to visualizing spatial exposure data for comparing earthquakes. And Stephanie, the floor is yours. Your screen's already shared, so you can just go ahead.
Thanks for the introduction, and thanks for inviting me to speak. I'm excited to be here. Yeah, just kind of as a quick disclaimer, I'm by training primarily an economist, but I do interdisciplinary research. I also come out of an interdisciplinary PhD program. And in my PhD program, I actually also took classes in the natural sciences. So it's a program that combines natural science and social science coursework. And I in particular also took classes, PhD level classes in seismology. So I do have some background in seismology, even though I'm primarily an economist. And kind of in my work on looking at, from this economist perspective, at how do earthquakes actually affect societies and economies? What are the socioeconomic impacts of earthquakes? I was working a lot, obviously, with social scientists, but also with natural scientists. So the origin of my research was, how can we best use earthquake data to implement that in social science research? And that's the perspective where I'm coming from. And in that research, I kind of ran often into problems, and this is one of these projects that kind of came out of this, that these different disciplines tend to not have ideal communication channels. So very often the things that social scientists think are important and want to talk about are not the things that natural scientists think are important and want to talk about. And therefore there's some mismatch in how certain kind of natural science concepts are implemented in the social sciences. And some of my research projects try to address these kind of basically communication problems and how to improve on using natural science data in the social sciences. And in this project in particular, I'm working on visualizations, how to use earthquake data to create visualizations that are really useful for a general audience, but also for social scientists in their research and their interpretation of that relevant data. And basically, one second, it doesn't go through. So basically, in a way, it can be thought as a methods paper of how to transform the data, how to create these visualizations that I believe would be helpful to kind of clear up certain misconceptions about earthquakes and earthquake data interpretation. And the way we're going to do this is with 3 example earthquakes. So in 2010, you probably have heard of the 2010 Haiti earthquake, which was in January of 2010. And it was a devastating event. It still, to this day, has catastrophic effects on the Haitian society and the economy. During the event, many people died. There are estimates of up to 200,000 people that died in the earthquake. Then about a month later in Chile, there was another earthquake that was also very big, also had many fatalities, about 1,000 people died. But compared to the Haiti event, it didn't have the same catastrophic impacts. And then the third earthquake that I'm using is a New Zealand earthquake that you might not have heard about. It wasn't as kind of well known as the Christchurch earthquake, that was a year later, but it was still quite a big earthquake, but there were no fatalities, which was in September of the same year. So the Haiti and the Chile earthquake, I assume many of you might have heard about. And the comparison of those 2 earthquakes is basically where I'm starting out of with this project. So kind of the first question is like, what's the problem? What's the issue that I'm trying to address here with creating kind of new visualizations of data? So these are news snippets of reputable outlets that talked about these 2 big earthquakes of 2010, just January, February, a little bit more than a month apart. 2 major earthquakes happened in Haiti and Chile, and it kind of was natural almost to try to compare the 2. And a very common comparison was to talk and try to explain why the impacts in Haiti were so much worse than in Chile. Chile also had bad impacts. It was still quite devastating in Chile, but it wasn't as catastrophic as the experience that Haiti went through. And you can see highlighted a couple of these kind of parts out there that were that the Chile earthquake was hundreds of times more powerful than the one that struck Haiti, or released about 500 times the energy of the magnitude 7 quake that hit Haiti, and so on. So there's a very common tool to compare earthquake. Let's just go back for 1 second to highlight something. In this table, you might notice that I did not list magnitude. I assume most of you are familiar with seeing kind of Richter scale magnitude of earthquakes. Whenever you hear something about earthquakes, people do talk about magnitude. And that's also in these new snippets that we have here. People do compare earthquake magnitude of different events with each other. And that's what this number, this 500 times stronger in Chile refers to. They talk about magnitude. And the reason why I didn't show you magnitude is because I think that is one of the big problems in earthquake communication, that there is way too much focus on earthquake magnitude when it actually isn't the thing that's relevant for a general audience. For kind of quick background on what is earthquake magnitude, that is the amount of energy that's being released during an earthquake, but that energy is released deep down in the earth. If we think about an earthquake, most of you probably interpret earthquake as kind of a synonym to the ground shaking, the ground moving. That's what earth and quake kind of refer to. It's the ground moving. That's not what seismologists or natural scientists in generally think about when they talk about earthquakes. What they mean with earthquaking, it's the planet Earth quaking, the planet Earth kind of having movements and ruptures. So magnitude refers to that energy that's released inside the planet. That can be kilometers down below the surface. And the kind of ground shaking that generally people are interested in and think about as kind of relevant, because that's the thing that destroys stuff on the surface, that is only one aspect of an earthquake that seismologists would study about an earthquake. So magnitude is not really a good proxy for earthquake shaking. So one big message that I have in my research, not necessarily that strong in this project, but in other ones, is to kind of move away from talking about magnitude and instead talk about earthquake shaking, because that is the actual physical hazard of interest for a general audience or a social scientist. But in these newspaper snippets, even though they're trying to explain these different impacts that happened in Haiti versus in Chile, they still talk about magnitude. They talk about this natural science concept of energy being released, but that energy is absorbed through whatever kind of ground the waves, the seismic waves travel through. There are different kind of attenuations, at different depths. There are a lot of different factors that matter for what kind of ground shaking would actually be experienced on the surface. Generally, comparing and benchmarking earthquakes to each other is a very popular tool to try to illustrate what is going on in one event versus another, and to highlight issues like in Haiti being a very poor country and how an event like the 2010 earthquake can be really devastating for society like that, because they're not prepared, they don't have the means and resilience to kind of just bounce back from that. Versus Chile, a much richer country, much wealthier country than Haiti, and much better prepared for earthquakes. They have a much better building infrastructure. And one big argument that kept coming up was the fact that Chile was so much better prepared than Haiti, and that was part of the reason why they fared so much better. But if we just focus on magnitude, this 500 times stronger event, we're actually kind of misreading the situation of what's happening here. And that's what I'm trying to show with my work here. So we want to compare earthquakes because we can learn from one event compared to another. There are lessons learned in there. And people in these comparisons that they make in here, they make very correct statements, but they can convey the wrong message to a general public or to social scientists, like focusing on the difference in the strength of magnitude. Despite kind of the small problem that comparing a magnitude, for example, here of 7 in the case of Haiti and 8.8 in the case of Chile, is not for everyone easy to understand why that means a 500 times difference in actually energy release, because it is a magnitude scale. But besides that, also just generally the energy released in an event is not the crucial fact. The crucial thing is the shaking on the surface. So let's go deeper into one of these articles. Here's a paragraph that actually does try to talk about surface shaking. So it starts out with the question, why didn't the earthquake, the Chile earthquake here, do 500 times more damage than in Haiti? And then there are 3 paragraphs. I'm quickly going to go through them to just highlight what's happening. Big earthquakes affect larger areas than smaller ones, but don't necessarily knock down more buildings. That is partly because subduction zone earthquakes occur offshore and the strength of the shaking diminishes quickly with distance, so says Seth Stein, a geophysicist at Northwestern University. A large earthquake close by does more damage than a huge one a little further away. And the Haiti earthquake was relatively shallow, whereas the Chilean one was deep. Just as damage reduces with horizontal distance from the fall, it also attenuates with vertical distance, says Scott Ashford, head of the School of Civil and Construction Engineering at the Oregon State University in Corvallis. Another factor is the speed of the ground shaking. Giant earthquakes, says Oakle, tend to put much of the extra energy into slower long period vibration rather than adding to the strength of the 1 Hz frequency vibrations most effective at knocking down walls. You get a kind of saturation, he says. A larger area is affected, but the intensity does not necessarily grow. I don't know how that is for you, but I took PhD level seismology classes. This is painful to go through. This is not easy to understand. This is kind of giving extra natural science information that is very interesting in general. It is very relevant for seismologists and certain other disciplines in the natural sciences. It's not actually what seems to help us to understand the original question of why didn't do the Chile earthquake 500 times more damage than the one in Haiti? I'm kind of like really amused whenever I see these articles, how they're trying to pose this social question of trying to explain damages, but then they interview natural scientists who obviously give a natural science explanation, and they explain the details of their own expertise, where they know a lot of things and they can explain these subtle differences between different events. So essentially what they're trying to explain here is why the shaking in one event was different than the other. But what we actually do want to know is how it was different. And that is something that is usually not explained, but really relevant for interpreting the difference then in impacts. Just to help you a little bit kind of somewhat make sense of what I just went through, kind of a quick earthquake 101. An earthquake starts at the hypocenter. I don't know if you can see my pointer. Can you see my mouse or not?
Yes, we can.
Okay, good. So an earthquake starts at the hypocenter, somewhere deep underneath the ground. And then there is a general rupture area where the fall, where you have 2 tectonic plates that move. So this rupture area is what's moving. And from that area, there are seismic waves radiating out. And then what we're as kind of social scientists or general public are interested in is actually just what's happening on the surface of the Earth. So the waves that travel up and get here, that's what we are interested in. So the depth of the hypocenter really matters, because the further the waves travel, the more they kind of lose strength. How deep is an earthquake matters for how strong of a shaking we have. What kind of soil it goes through matters for also how it attenuates, how it loses strength. The position of the epicenter is just a projection to the surface. Depending on the angle of the fault, that can actually be a little bit off where we have the strongest shaking. So if you see here, the strongest shaking is a little bit to the side of the epicenter actually in this illustration. We have a fault surface trace. That's just where that particular fault touches the surface. That doesn't mean that the earthquake is happening straight underneath the fault surface trace. And most importantly, earthquakes happen where we have these tectonic plates meet. And a lot of tectonic plates meet along coastlines. So a lot of earthquakes actually happen out in the ocean. So if you imagine having some big water body out here, well, then the actual shaking that we see on the ground is just somewhere far off over there. So depending on the location of the epicenter, if that falls kind of in the ocean, in a water body, the actual shaking experienced on land that people would observe can be much weaker. And that's, for example, also what they talk about for the Chile event, where the strong area would have been kind of out in the ocean, but that there was the ocean, so that didn't actually bother anyone. But that's not actually something that you need to know. All you really need to know is just how did this shaking on the surface look like? And this is the example for the Haiti earthquake. So luckily, the USGS, the United States Geological Survey, they produce these shake maps. Those are maps that show us the shaking intensity for more or less all earthquakes. If we have some time at the end, I can talk a bit more about different kind of ways to measure shaking, because shaking doesn't have just one physical size. So I'll just mainly refer to shaking intensity, but I will also be using peak ground acceleration as the measure that I implement here, but it's generally there are other measures possible, just to make sure you're aware of that. So these maps exist, and the data of these maps is what I'm using in my suggested visualizations. So basically, how should we approach this to kind of get people to talk more about the how is shaking different instead of why is it different? First of all, we do want to compare earthquakes to be able to learn from them. But to do that, we need to clearly separate the geophysical part of an earthquake with the social component of it. And because we want to make conclusions about how much did the social aspect matter. So for that, we first need to very clearly present and compare the geophysical differences, in this case here, of shaking, before then going into the much more complex discussions on the social dimensions of an event. And mainly what I'm suggesting here are two different types of visualizations, one being about the geospatial comparison of shaking, and the second is exposure curves that I'm creating and to look at the data for social scientists, decision makers, in kind of a disaster context, global governments, local governments, or also a general interested public, or for example, data journalism. And I'm also creating an R package together with Emilia Cabrera, who's been a very, very helpful research assistant on this project. So the idea of this R package is to not just here kind of suggest the methodology of, oh, this is how you could create these visualizations. That would be way more helpful for people to then talk about earthquakes and interpret earthquakes, but to also kind of facilitate the implementation of these visualizations by providing an R package that automatically kind of uses the USGS data to create visualizations that I'm suggesting here. It's not completely ready yet. There are still some small problems we have that we're still ironing out, but hopefully will be released later this year. So the first kind of suggestion that I have that sounds very extremely simplistic and is this surprisingly kind of magic tool that no one has ever used yet, which is just putting the shakes maps next to each other. So if we want to compare, in this case, the Chile and Haiti event, for example, why not just put the two maps next to each other, also the New Zealand map? And this is an extremely simple suggestion, but no one has done that yet. So through all that, there are many different articles in news outlets, in academic journals and articles that have compared Haiti and Chile, and also to some extent New Zealand. But I've not found a single instance where someone has actually tried to put the shake maps of these events next to each other to kind of have a visual comparison of what actually happened there. Some of them have used one shake map if they're mainly about one event, and then just compared somewhat with the other one. They put in one shake map, but I've never seen two or more shake maps, not just for the Chile and Haiti comparison, but also in general. That is something that seems obvious, but people are not doing it. So the question is, why are they not doing that? It seems like it should be obvious. I'm sure it has occurred to many people to want to do that. And I'm fairly certain that the reason why they haven't done that is because as we kind of put them here together, those are the ready-made shake maps that you can download from the USGS website. I think now they look a little bit different, but this is when I downloaded them. And the thing that comes apparent when we look at that kind of seems like maybe the New Zealand earthquake could have actually been that kind of biggest one, just looking at the colors and the size. But if we take a closer look, we can see that the scale of the size here are not the same. So we have a different spatial scale on every single map because they're produced as an individual event map. And if we would zoom out, there's no point if you just want to look at New Zealand, why would you zoom out further to have the same scale as in Chile if you're just looking at one event? But if we want to compare events with each other, we do want to have the same spatial scale. And for that purpose, there are no ready-made kind of visualizations available. And that is the thing that I'm mainly suggesting here is we need to put the shake maps next to each other, but not just next to each other. They also need to be at the same spatial scale and color scale. Right now, the USGS maps are now mainly kind of tuned to the same scale. In the past, they also used to have event-specific color scales. So that has been fixed now through the USGS website, but still the spatial scale doesn't match up. And it wouldn't make sense for them to standardize it to always be at the same level, because if you just want to look at one event, you could, like for Chile, that would be a really big image if you don't want to kind of decrease the size of New Zealand drastically. So to rescale them to the same spatial scale for the comparison that I want to do here, I've created these visualizations for Chile, Haiti, and New Zealand and put them all on the same color scale. And that now kind of really helps us to start really think about this difference in how was the shaking different from one event to another. So in Haiti, we can see we have clearly the strongest shaking here, the very intense yellow color in this area, which also actually happens to be Port-au-Prince, where the city's capital was. So that's part of why there was so much destruction happening, because the strongest shaking was in very densely populated area. But in Chile, we can see there's fairly strong shaking in a very big area. That is huge compared to the spatial size of Haiti or New Zealand. So in terms of spatial extent, clearly Chile was the biggest. But in terms of shaking intensity, Haiti was the biggest. And then New Zealand had kind of stronger maximum shaking intensity than Chile, but spatially it was smaller than the two others. So that's the first kind of simple suggestion. Let's just look at the maps at an appropriate spatial scale and color scale that allows us to compare them with each other. Some of you might notice, because we're creating this R package, that those are not actually our visualizations. Those visualizations have been done in MATLAB. So that was the first kind of version of the code. We are now rewriting the code to be in R, and I'll just show you. This is the visualization that we have for Haiti, where we also made sure to use a color scale that kind of really matches up with what we want to have kind of the blue background for this year round. The one problem that we still have, if anyone has any suggestions there at the end or wants to email me afterwards, I'd be very happy to talk about that more, is that there's no standardized way right now to actually plot individual maps at similar spatial scales. Obviously, if we kind of save an image, we can't save in vector format because that doesn't actually have a size that we could then compare two images with each other. We need to save it on a pixel format. Right now, we're trying to figure out how to like really kind of assign basically individual pixels to have a specific spatial interpretation to then be able to plot them and include them in some document next to each other where the individual maps can be compared through their spatial size. So that is unfortunately more complicated than we had hoped. If anyone has a suggestion there, I'd be very happy to talk about that more. But this is how they're going to look in the end through our R package. And kind of thinking back of these comparisons of the different maps, that helps a lot. This is really good for a general audience, for people that might live in earthquake-prone areas to think about earthquakes. If we want to dive deeper into, okay, which one was stronger now? How can we define one event being stronger or weaker than another in terms of pure shaking? It actually helps if we remove that spatial component and just look at the individual data points. So to remove the spatial component, I define what I call the area point exposure. So it's the area that is exposed to a specific shaking level S. So we're just adding up all the different areas that the size of the areas in square kilometers that have the particular level of shaking S, and that is our area point exposure. We can then plot that. So what we have here on the x-axis is our shaking level, the shaking intensity, here measured in peak ground acceleration in percent g, so percent of the gravitational force. And on the y-axis is it's a log scale for the area exposed in square kilometers to that particular level of shaking. And if we do that, we can clearly see, if we compare New Zealand and Haiti, that for any particular level of shaking, New Zealand had less area exposed to that level of shaking than Haiti had. So here it's actually fairly easy. We can say that Haiti was a stronger event than New Zealand in terms of shaking. If we look at Chile, it gets much more complicated. For the lower values, it had more area exposed, but then at the higher values here, it has less area, and then it kind of really doesn't have any area exposed to these extremely high shaking values where Haiti still has quite some relevant spatial exposure. That's the first way to look at that. But to then interpret the data in a kind of, I think, more convenient way is to not just look at the area point exposure, but to use exposure curves. The idea is we don't just want to know at any particular level of shaking how much area was exposed to that level, but we want to know how much area was exposed to that level or higher. Maybe we don't really care that much about how intense in particular it was. Maybe if we say a shaking level here of 60 is where it's really strong, and anything above that, anything kind of gets decimated anyways. So, which is not really true, but we see kind of intense damages in that area definitely. But we just want to know how much area was exposed to that level or stronger. So we can calculate that as our exposure curves. You can think of that as like the integral of the surface area underneath these curves here from the right. Or here, the shaking exposure curves is the area exposed to a specific level of shaking or higher than that. And if we plot that, we have the shaking exposure curve here, which is smooth. It's a monotonous function because we don't have we can kind of reduce the area if we keep kind of lowering the shaking level that we're interested in. So here now, this is what I think gives the most convenient way to actually visualize the data for someone to interpret what has been happening in two events compared to each other. So you can clearly see again the maximum shaking of the three different events, where Haiti had the strongest maximum shaking, then New Zealand, then Chile. And as we decrease the shaking level threshold for quite some time here, Haiti keeps having the most area exposed. But then at about 60% G is where Chile starts to take over. So if we're kind of just using a threshold of 60% G, then that's where Haiti and Chile had more or less the same amount of area exposed to strong shaking. If we say we just want to know kind of any shaking level above 30, for example, then Chile had the most area exposed to a shaking of 30 or higher of those three events. Depending on what in particular you're interested in, you might want to be interested in different thresholds. It depends on the different types of buildings, what kind of shaking levels would cause what kind of damage. And we can now define here that one event A is stronger in terms of shaking than another event B if the shaking exposure curve A is weakly greater than the exposure curve B, and for at least one shaking level X, it's strictly greater. So a comparison that we couldn't do from just looking at the shake maps next to each other. With these graphs, we can fairly easily visually inspect them and say if one event was stronger in terms of shaking than another one. And that is basically kind of a main suggestion that I have to include in these articles, where they don't seem to be shy to go into technical details. I know that kind of this graph might not be that easy to interpret for a layperson, but social scientists or decision makers should be able to kind of use these graphs in a meaningful way to interpret earthquake data. And also, I believe many people that live in earthquake-prone areas could easily get accustomed to reading graphs like that. If we want to look at kind of other ways to potentially remove kind of the shaking component, we could instead use something like the average shaking by area. So we could use the average shaking in the strongest, for example, 100 square kilometers, 1,000 square kilometers, and so on. And but the problem there is that it doesn't allow for an easy translation into a population measure. So far, this is just purely a geophysical measure that allows us to compare shaking. But now the next step is we actually want to look at population exposure. We're not just interested in area exposure. So one big difference that often came up between Chile and Haiti was that Haiti was really hit in the most populated area of the country. That's where the strongest shaking happened. So large damage does happen where the social exposure and the strong shaking do overlap. And to kind of look at that, we need to combine shaking data with population data. And the data that I'm using here and that I'll include in the R package to kind of for the automated generation is the gridded population data of the global population of the world, the GPW data by season. And the first way we can visually compare it is to use a bivariate Chloropleth map. So we have down here the legend where we have population as kind of on the blue scale from kind of a light blue to a darker blue, and shaking intensity is on the red scale from kind of white to a darker red. And if something is exposed to both of them, then it ends up kind of being in this purple area. And that's where we can see here for Haiti, this really dark purple area where both shaking and population were really high. That is one way to visualize that. There's still a lot going on. It's still not the easiest to interpret. Another way that is not ideal for the 2D version that I'm presenting it right now are Bivariate 3D maps. Those are great if you have, for example, an online tool where you have an interactive visualization where people can then rotate them around and inspect them in more detail. So they're right now not matched in terms of the height of population, but we have basically on the third dimension population, it's a map of the two different countries. Left is Chile, right is Haiti. The peaks, kind of these skyscrapers, are the population densities in the different areas. And the color scale is the shaking exposure, where we again kind of can see here, this peak here, this skyscraper is very red. This is where you have the really high intensity shaking and also really high in population density. Those are not the easiest to interpret in this format, but I didn't want to kind of switch back and forth between an interactive visualization. So that's kind of basically a suggestion for if someone publishes on a website where they can include interactive visualizations, that would be a good tool for people to be able to manipulate that and really kind of look at the data in more detail. I think it's something that people could be very interested in and playing around with. Instead of using maps, we can again use exposure curves and look at not the shaking exposure curve, but population exposure curves. So the idea here is to use the exact same concept as before, but instead of always saying how much area was exposed, we're using the how much population was exposed to first each particular shaking level. And here now for the population exposure curves, the cumulative population exposed to the level or higher. And that again allows us to kind of rank events in terms of whether they had a stronger population exposure or not. So one event A had a stronger population exposure than another event B if the population exposure curve A is weakly greater than the exposure curve B, and for at least one shaking level X is strictly greater. And to put them all together here, so we have the area point exposure in the top left, that was just the area exposed to each particular shaking level. On the right, we have the shaking exposure curves, the cumulative area exposed to any shaking level or higher. And on the bottom, we have the same thing for population exposed. So we have population exposed to each particular level of shaking. And on the bottom right, we have the population exposure curve, the cumulative population exposed to a particular shaking level or higher. So if particularly now, if we compare the shaking exposure curve and the population exposure curve, we can see that in both cases, clearly Haiti is a stronger event than New Zealand. It actually kind of the difference between the two events increases when we look at population versus just shaking. And if we look at the comparison of Chile and Haiti, then in the shaking, we saw that at a threshold of 60% G is where Chile started to be spatially larger. But now for population exposure, we actually have to go down to 40% G, where Chile ends up having more population exposed. So the difference of why, this kind of to answer this question of why did the earthquake in Chile not kind of create 500 times more damage than in Haiti, even though the magnitude would suggest that it should be 500 times stronger, we can fairly easily answer this with the shaking exposure curve and the population exposure curve. Already from the shaking exposure curve, we can see that, well, Chile wasn't clearly stronger. It depends on how you want to define strength, but there isn't a clear event that was stronger. And if we include the population exposure, we can see that that even further moved kind of the problem towards Haiti because there were just way more people in the high shaking areas than there were in Chile. So that's basically my suggestion is we need to move away from kind of not just one, but paragraphs, these 3 paragraphs like that on the right side towards graphs like that one on the left, and then maybe some sentences that try to highlight the differences here, like highlighting what is the maximum shaking difference, where is the threshold if they do cross each other, where they do cross, and if they don't cross each other, really highlight how, oh, this event is actually clearly stronger than another one. So that's kind of the main suggestion that I have in here. To summarize that, these are the visualizations that I will include in the R package that I'm writing with Emilio Cabrera. So there will be kind of simple functions where people just provide the link to the USGS website of the particular events that they're interested in. Can be kind of any number of events, and it will then automatically create the maps, one function for the maps, and then different functions for the shaking exposure and the population exposure curves that I think can really help to facilitate better communication of earthquake data, to interpret different kind of events for decision makers, for data journalism, and for social scientists in interpreting data, and then looking at kind of more complex social aspects of, so why did it go so bad now in Haiti versus in Chile, where obviously the difference in the social aspects, that Chile was so much better prepared. Haiti had a very bad building infrastructure. There were many problems in the response to the earthquake. It was very unorganized. There was a lot of corruption, very problematic also NGO involvement that didn't kind of allow sometimes to have local people employed versus they kept kind of bringing their own people from outside. There were many things that went wrong in the response, and that is very important to learn, but we can only learn clear messages about these social dynamics if the natural science side is actually communicated well, and we know what that natural science difference actually is, to then say, okay, for that difference, Haiti, it's not that surprising anymore that Haiti was doing so much worse than Chile. And that is it for my presentation. So I'm happy to answer any questions or hear your comments and thoughts on my presentation. Thanks, everyone.
All right, great. So we're opening the floor for the questions and Q&A session. So if you want to ask a question, you can just raise your hand, or just, it's not a lot of us, you can just go ahead and unmute yourself and, you know, ask a question. Erica.
Erica?
Yes.
Hi, that's great. Thank you so much. Sorry, I joined a bit late, so I may have missed this, but I wondered if you could say a little bit about if you've had any sort of talks with decision makers about what they would use this kind of information for, and how, you know, what kind of communications it would be incorporated into and how it would improve things.
No, I've not actually had discussions with decision makers themselves. It's mainly kind of my, I guess, personal audience is more out of like social scientists, and I guess kind of to go to the beginning, so to have kind of basically articles like these that in a way, I guess, data journalism that are writing about these topics and comparing them to make it easier for them to present that information in a more conducive way that helps people to grasp the relevant differences. But if anyone has kind of connections to decision makers that would be interested in talking about that, I'd be very happy to chat with someone.
Well, I'm going to abuse the hosting spot, and then I'm going to ask a couple questions, if I may. One is kind of sort of conceptual, I guess. So I think I always found it like fascinating about like, can we do something to decrease the damage of the, earthquake? Because, we obviously cannot change like the physics and like, how strong the earthquake will be. It's a bit unpredictable, right? It depends on like a lot of things that probably out of the human's control, right? But can we learn from these lessons, for example, right? What actually strength mean of the earthquake, and how we actually measure damage of the earthquake for, kind of prevention lessons. So, for example, do not build buildings in this, like tall buildings in this area, because it might cause a lot of damage potentially, and things like that. So I know like a little bit that, for example, I don't know, San Francisco Bay Area, they don't have a lot of, something in this particular area because it's very risky because there might be an earthquake. But why other places don't learn from this lessons if they like potentially know that, there might be something very damaging going on?
Yeah, so there are many aspects to this question, or I guess my answer. Obviously, like earthquake engineers know that very well of how to assess the risk. That's where like all this information about a particular fall, like all these details that I'm like saying social scientists don't need to know. Earthquake engineers totally need to know that, for example. And they're very good in assessing different risk zones and kind of know how to build buildings that can withstand what kind of strengths and so on. However, building buildings in an earthquake-safe way can be very expensive. So that's not something that any country can afford. Also, like the case in Haiti, the fault that did rupture in Haiti, for example, was not really known before. And the reason for that is that Haiti is not the most earthquake-prone country, and it wasn't really a focus of, let's say, international kind of seismology efforts to map Haiti faults in great detail before that event happened. This has happened now. And Haiti is not rich enough to have its own kind of well-funded seismology institutes that just do it out of there might be something going on, which, for example, in a country like the US, is very well studied because they do have the funds of detecting fault zones and so on. So a lot of it is kind of how well can you study your own seismological profile, which is a matter of how wealthy the country is a lot of times. And building earthquake-safe buildings, again, can be very expensive. There are different like ways how that, in terms of a larger social science aspect, can matter, how that could help to learn, is if we think about measures that are more kind of wide set, like if you have a new law, for example, if you implement something like, for example, in Japan, you have earthquake warnings, you can have very short-term earthquake warnings, like a couple of minutes or even seconds. And that can be really helpful. I don't know if you've ever been in Japan. I've not, but I've heard the stories a lot of times. Like whenever there's an earthquake, like a couple of seconds or minutes before, everyone on their phones gets these alarms, and they all know, and then it just kind of, everyone is kind of prepared for it in like the last moments before the event happens. And also what they do is they slow down high-speed trains and they shut off gas lines, which can prevent the big damages. This warning is not enough to like do some major evacuations or something, but it's enough to save crucial infrastructure. And that can, like, if you keep a gas line from kind of exploding, that is a huge damage prevented, or a high-speed train from derailing. And these measures are very effective, but also, again, very expensive. But if you would say you implement something like that new, you could do a study where if you have kind of a more widespread implementation, you could do a study exactly through these methods by using objective exogenous natural hazard data from the shaking, and compare that to, once you have the implementation of that, before and after, kind of like a definitive study of how that changes damages that you observe over time. So that can help us to really assess the specific value that is saved from measures like that. I guess that's kind of the way that I would suggest and want to suggest people to use that kind of data. Instead of, because right now a lot of social science research does actually use damage data already. They measure the size of an event by how much was destroyed, but the amount that was destroyed is endogenous already to the kind of infrastructure, to the kind of society you're exposed to. So that also then matters for kind of long-term effects and stuff like that.
Yeah, that's exactly was my other question, like how, because it's like so endogenous basically on like the development of the place. Yeah, very interesting. Well, thank you so much for responding to my question. I have another one, but I'll hold it because we have one in the chat from Anastasia. Thank you for your presentation. Are there other earthquake event spares that you would be interested in investigating?
Can you repeat? Are there other event pairs? Okay.
Yeah, event pairs. Yeah.
Interesting. Yeah, no, obviously. So this is just the illustration of basically the method. Once that package is kind of released, it's possible to do that for any kind of events, and that's how I would want it to be used, for people to be like, so particularly if you live in an earthquake-prone area, people experience an earthquake, then they're very interested in, they're like, oh, was this stronger or weaker than last time? And then what they get is the number of magnitude, but the number of magnitude doesn't tell them what they personally experienced, how that was different, for example. So being able to look at these different shaking profiles of one event to another, let's say you live in Italy or something, in an area where you experience an earthquake once, and then again a couple of years later, or even the same year, to just be able to do that yourself for any two earthquakes that you are interested in. I guess another thing that I could have included here is also a comparison of, like, Chile had some of the largest earthquakes of the world in terms of magnitude and energy released, generally extremely earthquake-prone country, and comparing earthquakes in the same location just across time. I think that's something for which the tool is really useful and relevant, particularly in kind of the setting also, again, of decision makers, where they have one earthquake one time, a lot of stuff gets destroyed, and then they have another earthquake a couple of years later, a lot of stuff gets destroyed again. To be able to learn from, oh, did we implement certain measures in between? Did that help or not? I think really comparing how was the shaking profile can help them to interpret better and adjust their preparation methods better of what was effective and what wasn't. To see that as in comparison. So one comparison is at the same location across time, and the other comparison that's here is across kind of different locations, but in a similar timing setting, where we have, say, okay, the year 2010, we're not comparing two events that are 50 years apart and the world has changed over 50 years of how everything is. We're comparing events that are happening in the same year and at the same time span, but in different places of the world. So those are kind of the two ways of how I think it's really useful to use that method, use these visualizations to learn from comparing events. the reason why I picked those ones in particular is, I mean, I started out my research, my PhD in 2011. So it was like a year after those events happened. And I actually also had two of my peers in my PhD program. One of them was in the Haiti earthquake and the other one in the Chile earthquake. And that was quite interesting. We talked a lot about these earthquakes. So that's why I personally picked those earthquakes. But you can do that basically for any earthquakes you might be interested in.
And there was another question in the chat, more like a technical, well, Anastasia, thanks you for the extensive response. But there is a question from Thor. Is the data and replication code might be available anywhere? And again, thank you for your talk.
The code will be available, not just yet. If you're particularly interested and kind of want to get it sooner, if you have some application, feel free to send me an email. I'm happy to kind of chat with you and maybe share something also earlier before it's officially released. But yeah, it will definitely be published as an R package to be able to apply that to kind of any events that you're interested in. That's kind of the whole point of the project.
Very cool. Okay, well, I'm going to use the couple minutes before anyone maybe writes another question in the chat. I had another more technical question about, you said that it's hard to compare like two maps between each other because and maybe I'm misunderstanding, but is it because the kind of zooming is different in a sense, like Haiti is so small and like, for example, Chile is like so large and the area is much bigger. Is it because of that, or
you mean in terms of what I said, that I'm having a hard time to create this in R?
No, you mentioned that there is like a problem with comparison, that you need to use pixels.
Okay. Yes. No, so that's the, well, like here, for example, they're not at the same spatial scale. So you need to have them at the same spatial scale, which I did produce here in MATLAB, but with some, I'm going to call it a dirty trick, which you might also notice, like the font is also different because I just scaled them smaller, like based on how they scale to each other. I just scaled the image differently, which is not ideal for like the final package output that we want to have. We want to have the font kind of match up. We just want to have the map adjusted accordingly and not everything else. Like if you'd have, I mean, this is already kind of fairly extreme differences of the spatial extent in Chile versus in New Zealand, but you could imagine even smaller earthquakes. If you have very weak earthquakes or something, they might be even spatially smaller maps. But the problem is, if you save these images, like they're not printed out. If you have like scales used to be something you print, and you have this distance and how many meters, like how many centimeters refer to how many kilometers or something, and that's not how computers work. Computers, like you don't have that same comparison. If you have any image that's vector based, like a PDF, then it doesn't have any particular size. So the way around is to use images that are pixel based, and then say each pixel basically refers to, let's say, 0.1 degrees, and have that be represented in the data. But there doesn't seem to be any standardized way to implement that in R. Like you could, or any other software that I kind of like know how to code in. And what you can do is kind of plot them all on one map. Then you have an entire world map where at one end you have Chile and then Haiti, but then I don't need the entire world. I just want those two maps. And you might also want them separate, like you don't necessarily want them in one image. So having them as separate images, but saved in a way that they map to each other spatially is a very complex endeavor, actually. And yeah, so I'm dealing with using ways to really assign individual pixels now. But yeah, if anyone has ideas on how to approach that's kind of in terms of the data science aspect, the most challenging task right now that we are trying to resolve.
Is it possible to do like a grid, like to kind of treat it as like, like, how all like a spatial RDD stuff works when they like use
it is a grid. It is a grid. That's basically the idea. It's a grid, but as once you turn the image in, when you plot it and you save it as a PNG, it is a complicated way to make sure that the writing on the axis is the same if you assign the pixels to be a specific distance. That's kind of the main. So basically we need the pixels in here to be based on the geographic distance of how many degrees here it is. And then we need extra pixels on the left for the axis and on the right for the color scale that are always the same number of pixels, something like that. That's kind of the way we're trying to approach it right now, which seems weirdly too complicated. There should be some easier way to be like, I want them to be at the same spatial scale, save them as a PNG, but that has not worked so far.
Thank you all for being here. Thank you so much again to the speaker, the host, and everybody who asked questions. And we look forward to seeing you again sometime soon. Thanks and bye-bye.